This is another video that I want to cover with you in our thermodynamics lessons, and I think I skipped it and did not include it in the previous video, so I want to solve a few of such questions in this video. So here is the first one, so what we're going to look at. So in the first one, they say that a silver bullet of mass 2 gram impact a well-insulated wall at 200 meters per second. And they give you the specific heat of the bullet. So the specific heat of the bullet is given. And then how much does the temperature of the bullet increase upon the impact? And we're going to assume that all the heat that was all the energy that was lost by the bullet is going to go into the heat energy of that bullet. So we have 1/2 mv squared. So that is so I have the kinetic energy of the bullet that is going to go into the heat energy of the bullet. So that energy is going to be transferred into mc delta t. So all the energy that the bullet had as motion energy, kinetic energy, went into the heat energy. So the mass of the bullet is the same on both sides. I can cancel that part. Then I have 1/2. The velocity of the bullet is 200 squared and equals to specific heat of the bullet is 240. And I'm looking by how much its temperature is going to change. So the change of the temperature is equal to 200 squared, which is 4 and 4 zeros, and divided by 2, and I have to divide by 240 both sides as well. So I also can cancel a 10 and a 10 from both sides. I can cancel a 2 and a 2, so that's going to be 2000 divided by 24. I can also divide them by 4 and by 4, so that will give me 506. So 500 divided by 6 gives me 83.3 degrees Celsius. So that's by how much the temperature will increase. It's not the final temperature. It depends on what the temperature of the bullet was, but that's by how much the temperature of the bullet is going to change. In this question, I have 750 kilogram car is moving at 20 meters per second and applies the brakes to stop. So the car had kinetic energy and it loses the kinetic energy. So I'm going to assume that all that kinetic energy is going to go into the heat energy of the brakes. So this was for the car and this is the brakes. So the kinetic energy of the car is 1/2 and then I have mv squared. So that's the mass of the car. And on the other side, I'm going to have the heat of the brakes. So the mass is different, not the same as it was in the bullet. So I have m, the brakes, c, and delta t. So at first, they tell you the mass of the car, and they give you the mass of the brakes. And then they give you the specific heat of the brakes. So I'm going to plug in my numbers. So I have 1/2. The mass of the car is 750. And the velocity at which the car is moving is 20 squared. And then on the other side, I have the brakes, which is 15 kilogram. Specific heat is 450. And I'm looking by how much the temperature will change. So now if I calculate for delta T, I have the temperature is going to change of the brakes by 22.2 degrees Celsius. And again, this is not the final temperature, this is not the initial temperature, but that's by how much the temperature of the brakes changes. So if the initial temperature of the brakes was 10 degrees Celsius, then the final would be 32 degrees Celsius because the change of the temperature is equal to 22 degrees Celsius. Here's another problem and similar concept. So I have the car moving at 15 meters per second, stops, and the brakes were applied, and the brakes mass is given 20 kilogram, and specific heat of the brakes is given. I have to find the temperature increase in the brakes. So I have kinetic energy of the car is going to go, the energy is going to be transferred to the heat energy of the brakes. So I have 1/2. The mass of the car is 1000 because it's 1/2 the mass of the car, velocity of the car for kinetic energy, and going to the heat energy, which is mc delta t. and then the velocity at which it moves is 15 squared equals to, the brakes are, the mass is 20, the specific heat is 450, and I look for the change of the temperature. I'm gonna do little tricks right here to simplify my math. So I see that this one is 15 squared. So I'm gonna cancel 15 from both sides. So divide this by 15 and divide this by 15. So what's left is 30 and 20 and delta T. And on the other side, I don't have any of the two 15s left, only one of them left because I divide by one of the 15s on both sides. And then 1000 divided by 2 is 500. Then I see that both sides have 100 in them, so I'm going to cancel that 100 from both sides, and I have 6 delta T is equal to 5 times 15. I also see that I can divide by 3 both sides, so I have 2 delta T is equal to 25. So delta T, increase of the temperature, is going to be by 12.5 degrees Celsius. So the heat, the temperature of the brakes is going to increase by 12.5 degrees Celsius. In this question, they say a sample of 100 gram is the same as 1 kilogram of water is at 30 degrees Celsius in a colorimeter. Colorimeter is the device where the energy cannot be escaped if you mix two different substances. I should say not mix, but if you place two different substances at two different temperatures and they will reach equilibrium, and the energy in them is not going to be lost outside of the container. So that would be the colorimeter. And then you have 50 gram mass of zinc, and they give you the specific, on the temperature of it is 130, and they give you the specific heat of zinc. And they want you to find the final temperature or equilibrium temperature. So every time you have these questions where you're looking for equilibrium temperature, you would say the change of the heat in zinc plus the change of the heat in water is going to be equal to 0. That means zinc is going to lose energy and water is going to gain energy, and the total energy of the system is going to remain the same, because when you place them in contact with each other, they had a certain amount of energy. They still have the same amount of energy at the end. They just distribute their energy. So the hot one gave the energy away to the colder one, or the cooler one. So if this is zinc, I'm going to have MC delta T for zinc, and I'm going to have MC delta T for water equals to 0. So again, this will be zinc, and this will be water. So if I plug in my numbers, mass of the zinc is 0.05, so that's 50 gram. Specific heat of the zinc is 390. And the change of the temperature, it's the final temperature, the equilibrium temperature that they reach together after being in contact for a while, minus initial temperature of the zinc, which is 130. And then plus the mass of the water, which is 100 gram, that's 0.1 kilogram. Specific heat of water, the one that I'm going to give you usually on the test, and I'm rounding to this number to 4200. Final temperature of them both, the equilibrium temperature that they reach, minus initial temperature of the water, and equals to 0. So I have zinc and I have water. Now if I do my multiplications and distribute the numbers, this is what I'm going to get. So if I distribute 19.5 and 420, and then I add them together, I get 439.5 T. And then if I distribute 19.5 and there is a negative sign, and 420 and there is a negative sign, so when I move them to the other side of the equal sign, I'm going to have them positive. So here I have both of them positive. So if I add those two numbers together, I'm gonna get 15,135. And then on the other side, I still have 439.5 T. So if I solve for T, T is equal to 15,135 divided by 439.5, and that will give me 34.44 degrees Celsius. So this was a video that I wanted to add to our thermodynamics video questions solved by me for you, so you learn from the examples when I'm solving them. And if you find in the future more questions in the lessons that we have that you might have not seen in the videos, please let me know. And thank you for watching, and I'll see you in the next video.